the history and engineering of common building materials. A complete technical overview for relaxation. Section 1. Introduction. Hello. Welcome to a gentle exploration of the materials that surround us in our everyday built environment. Over the next hour, we will take a slow, detailed journey through the composition, history, and technical specifications of the common building materials that form the structures we live and work in. This is not a rapid overview. This is a careful examination of substance, process, and specification. We will begin with the foundational materials, the things that support the weight of buildings. Then we will move through the materials that fill and finish spaces. And finally, we will explore the specialized materials that protect us from weather and provide insulation. There is a quiet rhythm to understanding how things are made. Each material has a story of discovery, refinement, and standardization. These stories are not dramatic. They are slow. They are meticulous. They involve incremental improvements over decades and centuries. They involve precise measurements and careful testing. And they are, in their own way, deeply relaxing to contemplate. As you listen to these details, you may find yourself becoming more calm. The specificity of technical information can be soothing. Numbers, measurements, percentages, and standards create a sense of order and predictability. The world of building materials is one of control and precision. Nothing here is left to chance. So settle in, get comfortable. We have much to explore and there is no rush. Time moves differently when we are learning about things slowly and deliberately. Let us begin. Section 2. Concrete. 2.1. Introduction to concrete. Concrete is perhaps the most fundamental building material in the modern world. It is everywhere, in foundations, in floors, in walls, in bridges, in parking lots. We walk on it, we build with it, we barely notice it. Concrete is a composite material. This means it is made of multiple constituents that work together. The primary constituents of concrete are cement, water, aggregates, sand and gravel, and often various admixtures. These components are mixed in specific ratios and then placed in forms where they harden over time through a process called hydration. The word concrete comes from the Latin word concretus, which means to grow together. This is accurate. The ingredients of concrete grow together. They bond at a molecular level. The result is a monolithic material, a single unified mass. Concrete is not the same as cement. This is an important distinction that many people misunderstand. Cement is a powder. Concrete is a mixture. Cement is to concrete what flour is to bread. You need cement to make concrete, but cement alone is not concrete. 2.2. Historical development. The history of concrete is surprisingly ancient. The Romans, over 2,000 years ago, created a material called opus cementicum. This was a mixture of volcanic ash, lime, and aggregates. Roman concrete was remarkably durable. Structures built with Roman concrete still stand today. The Pantheon in Rome, built around 127 AD, has a concrete dome that remains intact after nearly 2,000 years. However, the knowledge of how to make Roman concrete was lost for centuries. It was not until the late 1700s that modern Portland cement was developed. James Parker patented a cement in 1796. But it was John Smeaton, an English engineer, who discovered that certain types of limestone, when heated and mixed with water, created a durable binding agent. His work was conducted in the 1750s. The real breakthrough came in 1824 when Joseph Aspdin, also from England, patented Portland cement. Portland cement is so named because it resembles the color of stone quarried in Portland, England. The manufacturing process Aspen developed is fundamentally similar to how Portland cement is made today, more than 190 years later. The first significant use of Portland cement concrete in construction came in the mid-1800s. In 1848, a French gardener named Joseph Monnier created the first reinforced concrete. He added iron rods and wire mesh to concrete to increase its tensile strength. This was a critical innovation. Unreinforced concrete is strong in compression but weak in tension. By adding steel reinforcement, Monnier created a material that could handle forces in multiple directions. In the early 1900s, reinforced concrete began to be widely adopted for building construction. This material allowed for the creation of tall buildings, long-span bridges, and complex structural forms that would have been impossible with traditional materials like wood and stone. 2.3. Portland cement composition. Portland cement is manufactured from limestone, clay, silica, and iron oxide. These raw materials are quarried, crushed, and then combined in specific proportions. The mixture is then heated to approximately 1,450 degrees Celsius in a kiln. At this temperature, the materials chemically react to form clinker. Clinker consists of calcium silicates, which are the active compounds that give cement its binding properties. The clinker is then cooled and ground into a fine powder. During grinding, a small amount of gypsum is added. The gypsum controls the setting time of the cement. Without gypsum, cement would harden too quickly to be workable. Portland cement typically contains 4 main compounds. The first is tricalcium silicate, which accounts for approximately 40 to 60% of Portland cement. This compound is responsible for the strength of concrete, particularly in the first week of curing. The second compound is dicalcium silicate, which makes up about 15 to 30% of Portland cement. This compound develops strength more slowly, but continues to contribute to strength gain over months and years. The third compound is tricalcium aluminate, which accounts for 5 to 15% of Portland cement. This compound hydrates very quickly and can contribute to early strength, but it is also susceptible to sulfate attack. Sulfate exposure, which can occur in seawater or in certain soils, can cause deterioration. The fourth compound is tetracalcium aluminoferrite, which makes up about 5 to 15% of Portland cement. This compound contributes to later strength development. 2.4. Concrete mix design. The creation of concrete begins with mix design. This is a careful balancing act. The proportions of cement, water, sand, and gravel must be determined based on the required strength, durability, workability, and finish of the concrete. Water-to-cement ratio is critical. A typical water-to-cement ratio ranges from 0.4 to 0.65 by weight. A lower ratio produces stronger concrete, but concrete that is less workable and more difficult to place. A higher ratio produces more workable concrete, but weaker concrete. Sand, also called fine aggregate, typically makes up approximately 35 to 45% of concrete by volume. Sand particles range in size from approximately 0.1 millimeters to 2.4 millimeters. The size distribution of sand particles affects the workability and strength of concrete. Coarse aggregate, which is gravel, typically makes up approximately 40 to 50% of concrete by volume. Coarse aggregate particles range in size from approximately 4.75 millimeters to 37.5 millimeters, though the maximum size used depends on the application. Larger aggregate particles mean less paste is needed, which reduces cost and shrinkage. Cement typically accounts for approximately 10 to 15% of concrete by volume, or roughly 300 to 400 kilograms per cubic meter. Water typically accounts for approximately 15 to 20% of concrete by volume. 2.5. Strength development. Concrete strength develops over time. This process is called hydration. The hydration process is a chemical reaction between cement and water. The rate of hydration depends on temperature, cement composition, and water content. In the first 24 hours after placing, concrete typically develops 30 to 50% of its 28-day strength. This is why it is important not to load concrete too quickly after it is placed. At 7 days, concrete typically has developed approximately 70% of its 28-day strength. The 28-day strength is the standard measure used to specify concrete strength, though concrete continues to gain strength for years after it is placed. The strength of concrete is measured by compressive strength, which is typically reported in megapascals or megapascals. A typical concrete strength specification might be 25 megapascals for lower-grade concrete, 30 megapascals for standard concrete, and 40 megapascals or higher for higher-strength concrete. Concrete strength is tested using cylindrical samples that are 150 millimeters in diameter and 300 millimeters tall. These samples are cast and cured in the same conditions as the concrete in the structure. At 28 days, the samples are placed in a compression testing machine that applies a gradually increasing load until the sample fractures. The load at which the sample fails is recorded and divided by the cross-sectional area to calculate the compressive strength. 2.6. Curing and hydration time. Proper curing is essential for concrete to develop its full strength and durability. Curing means keeping the concrete moist and at an appropriate temperature during the hydration process. If concrete dries too quickly, the hydration process slows down and may stop altogether. This results in weaker concrete. Curing is typically maintained for a minimum of 7 days for normal concrete, though longer curing periods are beneficial. Methods of curing include keeping the concrete covered with plastic sheets, spraying it with water regularly, or applying curing compounds that form a membrane to prevent moisture loss. Temperature also affects hydration rate. Warmer temperatures speed up hydration, while cooler temperatures slow it down. In cold weather, concrete may need to be protected with blankets or heated enclosures to maintain adequate strength development. In very hot weather, concrete may be sprayed with cool water to prevent it from drying too quickly. 2.7. Reinforcement. Reinforced concrete combines the compressive strength of concrete with the tensile strength of steel. Steel reinforcing bars, called rebar, are placed in the concrete before it is cast. The steel and concrete bond together as the concrete hardens. This bond allows tensile forces to be transferred to the steel, which can withstand these forces much better than unreinforced concrete. Rebar comes in various sizes, typically ranging from 10 millimeters to 40 millimeters in diameter, though 12, 16, 20, and 25 millimeter diameters are most common. Rebar is typically made of mild steel, which has a yield strength of approximately 250 to 400 megapascals. The spacing and positioning of rebar within concrete is carefully designed based on structural analysis. Rebar is typically held in place using plastic chairs, concrete blocks, or wire ties to ensure that the steel is positioned correctly before the concrete is cast. The concrete cover, which is the distance from the surface of the concrete to the nearest steel reinforcement, is specified to protect the steel from corrosion and to ensure adequate bond. Concrete cover typically ranges from 25 to 50 millimeters, depending on the exposure conditions. 2.8. Concrete durability. The durability of concrete depends on many factors. Concrete in sheltered indoor environments can last for centuries. Concrete exposed to harsh environments may deteriorate much more quickly. Sulfate attack occurs when sulfate ions in soil, groundwater, or seawater penetrate into concrete and react with the aluminum compounds in cement. This reaction causes expansion and spalling of the concrete surface. To resist sulfate attack, sulfate-resistant cement can be used, which has lower levels of tricalcium aluminate. Carbonation occurs when carbon dioxide from the air penetrates into concrete and reacts with calcium hydroxide, which is a byproduct of cement hydration. This reduces the pH of the concrete and can lead to corrosion of embedded steel. Adequate concrete cover and dense concrete help to resist carbonation. Chloride penetration is a concern in marine environments or where de-icing salts are used. Chlorides can cause corrosion of embedded steel. Low permeability concrete, achieved through careful mix design and proper curing, helps to resist chloride penetration. Freeze-thaw damage occurs when water in concrete freezes and expands, creating internal stresses that can cause cracking and spalling. Air entrainment, which is the intentional incorporation of small air bubbles into concrete, provides spaces for ice to expand into and helps to prevent freeze-thaw damage. Section 3. Steel. 3.1. Introduction to steel. Steel is an alloy of iron and carbon. The carbon content of steel typically ranges from 0.1% to about 2% by weight. The carbon content and the processing of steel determine its strength and other properties. Steel is strong in both compression and tension, which makes it an ideal material for structural applications. Steel is also ductile, meaning it can deform significantly before breaking. This ductility is a valuable property because it allows structures to warn of impending failure through visible deformation rather than failing suddenly and catastrophically. Steel is recyclable. Old steel structures can be melted down and reformed into new steel indefinitely without loss of properties. This makes steel an environmentally responsible choice compared to materials that must be disposed of after a single use. Steel can be formed and shaped in many ways. It can be rolled into beams and plates. It can be forged. It can be welded together. It can be bolted. This versatility has made steel the material of choice for long-span structures like bridges and large buildings. 3.2. Historical development. The earliest forms of iron were meteoric. Meteorites contain iron, and before humans learned to smelt iron ore, meteoritic iron was the only source available. Artifacts made from meteoritic iron have been found dating back to 3000 BC or earlier. Iron smelting, the process of extracting iron from ore using heat, was discovered independently in several parts of the world. In Africa, iron smelting was practiced at least 3000 years ago. In Asia, iron smelting developed around 1500 BC. In Europe, iron smelting developed around 1200 BC. Early smelted iron was not pure iron. It contained impurities and had variable properties. It was also more brittle and less usable than bronze, which was the primary metal used for tools and weapons during the Bronze Age. This is why the transition to widespread use of iron took many centuries. By the 1700s, new smelting and refining techniques had been developed that produced better quality iron. The development of coke, which is a processed form of coal, allowed for hotter furnaces and larger scale production. The Industrial Revolution depended heavily on the availability of large quantities of relatively inexpensive iron. Steel, which is iron with controlled carbon content, was historically more difficult and expensive to produce than iron. The Damascus steel of the Middle East and the Wootz steel of India were famous for their superior properties, but they were expensive and could only be produced in small quantities. The Bessemer process, invented in 1856, allowed for the mass production of steel. This innovation was revolutionary. Suddenly, large quantities of steel could be produced quickly and affordably. The Bessemer process works by forcing air through molten iron. The oxygen in the air reacts with impurities in the iron, burning them away. This process generates significant heat, which keeps the iron molten. The process is simple and fast, but it was difficult to control the final carbon content precisely. Later processes, like the open hearth furnace and the basic oxygen process, provided more control over the carbon content. Modern steel production uses various methods, including electric arc furnaces, which allow for very precise control over the composition and properties of steel. 3.3. Steel composition and properties. The strength of steel depends primarily on its carbon content and its heat treatment. Carbon atoms fit into the spaces in the iron crystal structure, and they restrict the movement of dislocations, which are defects in the crystal structure. Restricting dislocation movement increases strength. Low-carbon steel, also called mild steel, contains less than 0.3% carbon. This steel is relatively soft and ductile. It is easy to weld and to machine. It is used for structural applications where moderate strength and good ductility are desired. Medium carbon steel contains approximately 0.3 to 0.6% carbon. This steel has higher strength than low carbon steel, but lower ductility. It is used for applications requiring higher strength, such as machinery and tools. High carbon steel contains more than 0.6% carbon. This steel is very hard and brittle. It is used for cutting tools and springs where hardness is important and the risk of brittle fracture is acceptable. Heat treatment can significantly affect the properties of steel. Heating steel to high temperature and then cooling it rapidly, a process called quenching, creates a hard but brittle structure. Tempering, which is reheating quenched steel to a lower temperature, relieves some of the brittleness and improves the balance between strength and ductility. Alloying elements can be added to steel to enhance specific properties. Nickel increases toughness. Chromium increases corrosion resistance and hardness. Molybdenum increases strength at high temperatures. Vanadium increases strength and toughness. Manganese increases hardness and wear resistance. 3.4. Steel grades and standards. Steel grades are standardized to ensure consistent properties. Various standards exist around the world. In the United States, the ASTM, American Society for Testing and Materials, publishes standards for different grades of steel. In Europe, the EN, European Norm System, is used. In Asia, different countries have their own standards, though there is increasing international harmonization. A typical structural steel grade might be specified as ASTM A36, which is a carbon steel with a minimum yield strength of 250 megapascals and a tensile strength of 400 to 550 megapascals. Another common grade is ASTM A992, which has a minimum yield strength of 345 megapascals and a tensile strength of 450 megapascals. Yield strength is the stress at which steel begins to deform permanently. Tensile strength is the maximum stress that steel can withstand before breaking. Ductility, often measured by the percent elongation at failure, indicates how much the steel can stretch before breaking. 3.5. Steel products. Steel is manufactured into various products for construction purposes. Structural shapes include I-beams, also called wide flange beams, channels, angles, and tubes. I-beams have a horizontal web and two horizontal flanges, creating a shape with high strength relative to weight. Channels are similar to half an I-beam. Angles are L-shaped. Tubes are hollow rectangular or circular sections. I-beams are designated by their height and weight per unit length. For example, a W200 by 52 beam is approximately 200 millimeters tall and weighs 52 kilograms per meter. The actual dimensions are slightly different from the nominal dimensions, but the nominal dimensions are what is used in designation. Steel plates are flat-rolled products that come in various thicknesses and widths. Plates are used for connection details, for fabricating built-up beams, and for many other purposes. Steel bars include solid rounds, squares, and flats. These are used for reinforcement in concrete, for connection details, and for various other purposes. 3.6. Connections. Steel structures are typically assembled through connections. Connections can be bolted or welded. Bolted connections use bolts, which are inserted through aligned holes in the steel elements. The bolts are tightened with nuts to create a connection that transfers load from one element to another. Bolted connections are relatively quick to install and can be disassembled if necessary. However, bolted connections require careful detailing to ensure that the bolt holes are properly aligned and that the connection has adequate strength. High-strength bolts, often made of alloy steel with a yield strength of 640 to 1,000 megapascals, are commonly used in structural applications. The size and grade of bolts must be carefully selected to match the forces being transferred. Welded connections join steel elements by melting them together and filling the space with additional molten steel from a welding rod. When cooled, the weld metal bonds to the base metal, creating a connection that can transfer load as if the elements were a single piece of steel. Welded connections can be very strong and efficient in design, but welding requires skilled workers and careful quality control. Welds can develop defects if the welding procedure is not properly controlled. Common defects include porosity, gas bubbles, lack of fusion, areas where the weld metal does not bond to the base metal, and cracks. 3.7. Steel in corrosive environments. Steel is susceptible to corrosion in the presence of moisture and oxygen. In corrosive environments, steel must be protected. Paint provides a barrier between the steel and the environment. Paint systems for structural steel typically consist of a primer coat, which bonds to the steel, and one or more top coats, which provide protection. Paint systems are specified based on the exposure conditions. More severe exposure requires more robust paint systems with more coats. Galvanizing is a process in which steel is coated with zinc. Zinc is more reactive than steel, so it corrodes preferentially, protecting the underlying steel. Galvanizing can be done by hot dip galvanizing, in which steel is immersed in molten zinc, or by electroplating, in which zinc is deposited electrically. Stainless steel is an alloy, steel containing chromium, which forms a protective oxide layer that resists corrosion. Stainless steel is more expensive than carbon steel, but is valuable in applications where corrosion is a significant concern. Section 4. Wood. 4.1. Introduction to wood. Wood is a natural composite material composed primarily of cellulose, hemicellulose, and lignin. Cellulose provides strength. Lignin binds the cellulose together and provides stiffness. Hemicellulose is intermediate in nature between cellulose and lignin. Wood has been used as a building material for thousands of years. It is renewable, relatively easy to work with, and has good strength-to-weight ratio. Wood can be cut, nailed, screwed, and glued. It can be shaped into various forms. It has aesthetic qualities that many people find pleasing. Wood is orthotropic, meaning it has different properties in different directions. Wood is strongest along the grain, weaker perpendicular to the grain. This anisotropy must be considered in structural design. 4.2. Wood species. Wood species vary widely in their properties. Softwoods, which come from coniferous trees like pine, fir, and spruce, are generally used for structural applications in building construction. Softwoods are relatively inexpensive and relatively easy to work with. Hardwoods, which come from deciduous trees like oak, maple, and cherry, are generally stronger and denser than softwoods. Hardwoods are used for finish applications, for flooring, and for applications requiring high strength or durability. Hardwoods are generally more expensive than softwoods. The distinction between softwood and hardwood is botanical, not based on the actual hardness of the wood. Some softwoods are actually harder than some hardwoods. Common structural softwoods in North America include Douglas fir, spruce, and pine. The properties of wood from these species vary based on the growing conditions and the age of the tree at harvest. 4.3. Moisture and wood movement. The water content of wood dramatically affects its properties. Green wood, which is freshly cut, contains significant water. As wood dries, it shrinks. The amount of shrinkage depends on the species and the direction of the grain. Tangential shrinkage, which is shrinkage along the growth rings, is typically greater than radial shrinkage, which is shrinkage across the growth rings. This differential shrinkage can cause warping and cracking as wood dries. Equilibrium moisture content is the moisture content at which wood does not gain or lose water from the surrounding air. This equilibrium content varies with the relative humidity and temperature of the environment. In most indoor building environments, equilibrium moisture content is in the range of 6 to 12%. Wood that is dried to approximately 15 to 20% moisture content is considered kiln-dried lumber. Further drying to 6 to 10% moisture content produces lumber suitable for interior finish applications, where dimensional stability is important. 4.4. Wood strength and grading. The strength of lumber is affected by growth characteristics and defects. Knots, which are areas where branches have been incorporated into the trunk, reduce strength. Slope of grain, which refers to the angle of the wood fibers relative to the axis of the board, affects strength. Rate of growth, which affects the proportion of early wood to late wood, affects strength. Lumber is sorted by grade based on these characteristics. In North America, the most common grading system for structural lumber divides lumber into grades like Select Structural, number 1, number 2, and number 3. Select Structural has fewer and smaller defects and higher strength. Number 3 has more and larger defects and lower strength. The strength properties of lumber in a given species and grade are published in design tables. These tables typically give the modulus of elasticity, which is a measure of stiffness, and the allowable stress in bending, compression, and tension. 4.5. Wood products. Solid lumber sawn from logs is one wood product used in construction. However, engineered wood products are increasingly used because they can provide more consistent properties and can utilize wood more efficiently. Plywood is made by gluing together thin sheets of wood veneer. The sheets are oriented with the grain direction alternating between layers. This cross-lamination increases strength and reduces the tendency to warp. Plywood typically comes in sheets that are 1,000 to 220 millimeters wide and 2,440 millimeters long, and ranges in thickness from 3 to 25 millimeters. Laminated veneer lumber, or LVL, is similar to plywood, but the veneers are oriented with the grain running in the same direction. This provides high strength along one direction. LVL is commonly used for headers and beams. Oriented strand board, or OSB, is made from wood strands that are glued together with the strands oriented in different directions in different layers. OSB is less expensive than plywood but has slightly lower strength. OSB is commonly used for sheathing. Glue-laminated timber, or glue-lam, is made by gluing together individual pieces of lumber with the grain running in the same direction. Glue-lam can be manufactured in larger sizes than sawn lumber and provides more consistent properties. Glue-lam is commonly used for beams and headers. 4.6. Connections in wood. Wood can be connected using nails, screws, bolts, or glue. Nails are simple and quick to install. A nail works by friction between the nail and the wood. The holding power of a nail depends on the diameter and length of the nail and the density of the wood. Screws have threads that bite into the wood, providing greater holding power than nails for a given diameter. Screws can be more expensive to install, but they provide a stronger connection. Bolts can be used for connections in wood to provide very strong connections. A bolt passes through aligned holes in the wood elements and is fastened with a nut on the far side. Glued connections, using wood adhesives like epoxy or polyurethane glue, can provide very strong connections if properly executed. Glued connections bond the wood itself rather than relying on friction or threading, and can distribute stress over a larger area. 4.7. Wood and moisture problems. While wood is relatively resistant to decay in dry conditions, it is susceptible to decay when exposed to moisture. Wood decay fungi can penetrate wood and break down the cellulose, causing the wood to lose strength. Wood rot is a serious concern in buildings with poor water management. Areas prone to wood rot include areas where wood contacts concrete, areas exposed to weather, and areas with chronic moisture problems. Protection of wood from moisture is critical. This can be done by using water-resistant finishes, by ensuring proper slope and drainage, by providing roof overhangs and flashing, and by maintaining gutters and downspouts. In some applications, pressure-treated lumber, which has been impregnated with preservative chemicals, is used. These preservatives inhibit the growth of wood decay fungi. The preservatives can be copper-based, like chromated copper arsenate, or copper-based formulations that do not contain arsenic. Section 5. Drywall and gypsum products. 5.1. Introduction to drywall. Drywall, also known as gypsum wallboard or plasterboard, is one of the most common interior wall and ceiling materials used in building construction. Drywall consists of a core of gypsum plaster sandwiched between layers of paper. Gypsum is a mineral, calcium sulfate dihydrate, with the chemical formula CaSO 4 times 2H2O. Gypsum occurs naturally in deposits around the world. It is mined and processed into drywall. Drywall is valued for its ease of installation, its fire resistance, its ability to receive finishes, and its sound absorption properties. Drywall is also relatively inexpensive compared to other wall materials. 5.2. Drywall composition. The core of drywall is made from gypsum that has been heated to remove most of the water, creating calcium sulfate hemihydrate or plaster of Paris. This material is then mixed with water to rehydrate it. The rehydration process causes the gypsum to crystallize, creating a solid core. Various additives are included in the gypsum core to improve properties. Starch and other binders improve the strength of the core. Fibers, including cellulose, fibers and glass fibers, increase the tensile strength of the core and reduce shrinkage cracking. The paper facing on drywall is typically made from a mixture of recycled paper and virgin fiber. Paper on one side, the face side, is white or off-white and receives the finish. Paper on the other side is typically gray or tan. Special paper facings are available for specific applications. In areas of high moisture, moisture-resistant paper, often called green board, is used. In areas where fire resistance is critical, fire-resistant paper with a glass fiber component is used. 5.3. Types of drywall. Standard drywall is the most common type used in typical building construction. Standard drywall is suitable for indoor environments with normal humidity and low fire exposure. Fire-resistant drywall, often called Type X drywall, contains glass fibers in the core and paper facings. This composition makes the drywall more resistant to burning. Type X drywall is required in many jurisdictions for areas like commercial buildings, stairs, and other fire-sensitive areas. Impact-resistant drywall is manufactured with additional fibers or with a thicker, stronger core. Impact-resistant drywall is used in areas prone to damage, like gymnasium walls or hallways in facilities like hospitals. Moisture-resistant drywall, often called green board, uses a moisture-resistant facing and may have additives in the core that resist moisture. Moisture-resistant drywall is used in bathrooms and other areas with elevated moisture. Mold-resistant drywall is manufactured with facings and core treatments that resist mold growth. This type of drywall is appropriate for applications where mold resistance is important. 5.4. Drywall installation. Drywall is typically installed by fastening sheets to the structural framing using screws or nails. A typical sheet of drywall is 1.6 millimeters to 15 millimeters thick and comes in sizes of 1,220 millimeters by 2,440 millimeters, or 1,220 millimeters by 3,660 millimeters. Screws are the preferred fastener for drywall. Drywall screws have a special design that pulls the drywall tightly to the framing and reduces the tendency for fasteners to pop. Screws are installed using a power drill with a screw gun attachment. Fasteners are spaced approximately 400 to 600 millimeters apart on walls and 300 to 400 millimeters apart on ceilings. Tighter fastener spacing on ceilings is necessary because gravity places greater stress on ceiling fasteners. Drywall is typically installed with joints offset so that the vertical joints of one row of drywall do not align with the joints of the row below. This offset improves the structural integrity of the wall. 5.5. Drywall finishing. After drywall installation, the joints must be finished using joint compound, also called mud. Joint compound is a mixture of gypsum powder and water that is applied over the drywall joints to create a smooth, even surface. The finishing process typically involves multiple coats of joint compound. The first coat, called the tape coat, is applied over the joint and embeds joint tape, which is a paper or fiberglass tape. The tape provides reinforcement and prevents the joint from cracking. Subsequent coats, called fill coats or topping coats, are applied to build up the level of the joint and to feather the edges so the joint is less conspicuous. Typically, 2 to 3 coats of joint compound are applied over a joint. After each coat is applied, the compound must be allowed to dry before the next coat is applied. The joints are sanded smooth after drying. Sanding creates dust, so dust containment and workers' respiratory protection are important during this process. 5.6. Drywall properties. The fire rating of drywall is measured using the ASTME 119 test, in which a wall assembly is exposed to a fire and the temperature of the unexposed side is monitored. The fire rating is expressed as the time in minutes that the wall maintains its integrity and keeps the temperature of the unexposed side below a certain threshold. 1-hour fire-rated wall assemblies are common. These walls contain Type X drywall, which allows the wall to resist fire for at least 1 hour. 2-hour fire-rated assemblies are used in more critical areas. Sound transmission class, or STC, is a measure of sound insulation. A typical drywall wall assembly with 65 mm studs, cavity insulation, and single layers of standard drywall on each side has an STC rating of approximately 38. Adding a second layer of drywall or using resilient channels can increase the STC rating to 50 or higher. Section 6. Insulation. 6.1. Introduction to insulation. Insulation is material used to reduce the transfer of heat between different areas. Heat is transferred by 3 mechanisms: conduction, convection, and radiation. Insulation primarily works by reducing conduction and convection. Conduction is the transfer of heat through material. Convection is the transfer of heat by the movement of fluids, air or liquids. Radiation is the transfer of heat by electromagnetic waves. Most insulation materials work by trapping small pockets of air. Air is a poor conductor of heat. By trapping air in small cavities, insulation materials create an effective barrier to heat transfer. The thermal resistance of insulation is expressed as an R value. R value is the thermal resistance per unit area, expressed in units of square meters, times Kelvin per watt, or square meters, Kelvin per watt. A higher R value indicates better insulation. In the United States, R value is often expressed in imperial units as square feet times degrees, Fahrenheit times hours per BTU. The relationship is approximately 1 square meter, Kelvin per watt, is equal to approximately 5.68 square feet degrees, Fahrenheit hours per BTU. The thickness of insulation is typically proportional to its R value. A 50 mm thickness of fiberglass insulation might have an R value of approximately 2 square meters Kelvin per watt. A 100 mm thickness might have an R value of approximately 4 square meters Kelvin per watt. 6.2. Types of insulation. Fiberglass insulation is the most common type of insulation used in building construction. Fiberglass insulation is made from thin strands of glass that are bonded together into a blanket or bat. Fiberglass is easy to install, inexpensive, and relatively effective. However, fiberglass can settle over time, reducing its effectiveness. Fiberglass can also become wet, which reduces its R value. When wet, fiberglass does not dry quickly, and it can support the growth of mold. Mineral wool insulation, also called stone wool or rock wool, is made from molten mineral material that is spun into fibers. Mineral wool is somewhat more expensive than fiberglass, but is more resistant to settling and moisture, and it has better fire resistance. Cellulose insulation is made from recycled paper that is treated with fire retardants. Cellulose is blown into wall cavities and attic spaces. Cellulose is inexpensive and has good insulating properties. However, cellulose can settle over time, and it is susceptible to moisture damage and mold growth. Foam insulation materials include expanded polystyrene, EPS, extruded polystyrene, XPS, and polyurethane foam. These materials have high R values for a given thickness. They are moisture resistant and do not settle. However, they are more expensive than fiber-based insulation, and some foam materials are susceptible to degradation by UV light and some chemical solvents. 6.3. Vapor barriers. The movement of water vapor through walls is an important consideration in building science. Water vapor can condense inside walls if the temperature drops below the dew point. This condensation can lead to moisture problems, mold growth, and deterioration of materials. Vapor barriers are materials with low permeance, resistance to water vapor flow, that are used to prevent water vapor from moving through walls. A typical vapor barrier has a permeance of less than 1 perm using imperial units. Common vapor barrier materials include plastic sheeting, foil-backed insulation, and kraft paper. These materials are typically placed on the warm side of insulation to prevent water vapor from the warm interior air from moving into the insulation and condensing. However, vapor barriers can also trap moisture if the exterior of the wall is also impermeable. Modern building science recognizes that some degree of vapor permeability may be beneficial to allow moisture to diffuse out of the wall assembly. Vapor retarders, which have slightly higher permeance than true vapor barriers, are sometimes used instead of vapor barriers. 6.4. Insulation installation. Batt insulation is installed by placing it between framing members and securing it with fasteners or friction fit. Proper installation is critical. Compressed batts have reduced R value. Gaps around penetrations can significantly reduce the effectiveness of insulation. Blown-in insulation is installed by machine. The insulation material is placed in a hopper, where it is mixed with air, and then blown into wall cavities or attic spaces through a hose. Blown-in insulation can fill cavities more completely than batt insulation and can fill around penetrations and obstacles more effectively. Spray foam insulation is applied by spraying. It expands after application, filling cavities and forming a seal around penetrations. Spray foam provides both insulation and air sealing, making it very effective but also more expensive. 6.5. Air sealing. While insulation resists heat transfer through conduction, air infiltration can transfer heat through convection. Air sealing, which means sealing air gaps in the building envelope, is just as important as insulation for reducing heating and cooling energy consumption. Air sealing is done using caulk, weather stripping, and other materials. Common places where air sealing is needed include around window frames, around door frames, around penetrations for pipes and wires, and at the interface between different building components. The air barrier should be continuous around the entire building envelope. Gaps in the air barrier allow unconditioned air to enter the building, significantly reducing the effectiveness of insulation. Section 7. Roofing materials. 7.1. Introduction to roofing. Roofing materials must perform several functions. They must shed water and prevent it from entering the building. They must have sufficient durability to last for decades. They must be able to resist wind uplift. They must be able to resist UV radiation. They must be able to accommodate building movement and thermal expansion. Roofing is the most exposed part of the building envelope. Roofing is constantly exposed to sun, rain, wind, temperature extremes, and air pollutants. The service life of roofing is typically shorter than other building materials. The slope of the roof affects the choice of roofing material. Low-slope roofs, slopes less than 4 inches of rise per 12 inches of horizontal run, or approximately 1 to 3, typically require membrane roofing materials that can be sealed at seams. Steep slope roofs, slopes greater than 4 to 12, can use shingles or other materials that shed water by gravity. 7.2. Asphalt shingles. Asphalt shingles are the most common roofing material for residential construction in North America. Asphalt shingles consist of a mat of fiberglass or organic fibers, typically cellulose or paper, that is saturated with asphalt and coated with mineral granules. The fiberglass mat provides structural reinforcement. The asphalt provides waterproofing and flexibility. The mineral granules protect the asphalt from UV radiation and weathering. Asphalt shingles are available in various styles and colors. Common styles include 3-tab shingles and architectural shingles. 3-tab shingles are relatively flat and uniform. Architectural shingles have a dimensional appearance with varying layer thicknesses that create a more textured look. Typical shingle dimensions are approximately 915 millimeters wide and 305 millimeters in height. Shingles overlap to create a water-shedding layer. Nails are typically driven through the shingles to secure them to the roof sheathing. A typical asphalt shingle roof is rated for a service life of 15 to 25 years, depending on the quality of the shingles, the climate, and the maintenance. In northern climates with significant snow load, algae growth, and freeze-thaw cycling, the service life may be shorter. 7.3. Wood shingles and shakes. Wood shingles and shakes are premium roofing materials made from cedar or other wood species. Shingles are sawn to relatively uniform thickness. Shakes are hand-split, creating a more rustic appearance with variable thickness. Wood shingles and shakes are valued for their appearance and their insulating properties. They are also renewable materials, though their environmental benefit depends on harvesting practices. However, wood shingles are susceptible to decay, insect damage, and splitting if not properly maintained. Wood shingles are more expensive than asphalt shingles and require more maintenance. The service life of wood shingles is typically 20 to 40 years with proper maintenance. 7.4. Clay and concrete tile. Clay tile and concrete tile are used in some regions, particularly where architectural styles favor tile. Clay tile is formed from clay that is molded and fired in kilns. Concrete tile is made from concrete that is molded and cured. Tile roofing is very durable, with service lives of 50 years or more being common. Tile is also fire-resistant and resistant to insects and decay. Tile has good aesthetic qualities and can contribute to the character of a building. However, tile roofing is heavy, often weighing 5 times or more per unit area compared to asphalt shingles. This weight requires substantial roof structure. Tile is also expensive compared to other roofing materials. Installation requires skilled workers. Tile can break if walked on. The expansion and contraction of tile with temperature changes can cause problems if the tile is not properly installed with adequate spacing. 7.5. Metal roofing. Metal roofing materials include steel, aluminum, and copper. Metal roofing can be installed in panels or in shingle form. Metal roofing is very durable, light in weight, and fire-resistant. Steel roofing is often factory painted with a durable coating to prevent corrosion. Aluminum roofing is naturally corrosion-resistant, but can be painted for improved appearance. Copper roofing develops a patina over time and requires no maintenance, but it is very expensive. Metal roofing can be noisier than other roofing materials when rain falls on it, though this can be mitigated through proper installation and insulation. Metal roofing can be slippery when wet. Metal roofing can expand and contract significantly with temperature changes, potentially creating gaps at seams if not properly designed. 7.6. Membrane roofing. Membrane roofing is used on low-slope roofs. Common membrane materials include built-up roofing, single-ply membranes like EPDM and TPO, and liquid-applied membranes. Built-up roofing consists of multiple layers of bituminous material, asphalt or coal tar, and reinforcing fabrics. The layers are built up to create a thick, durable membrane. Built-up roofing is installed by heating the bituminous material and spreading it over the roof deck. Built-up roofing can last 15 to 20 years or more. Single-ply membranes are sheets of flexible plastic material that are rolled out over the roof deck and sealed at seams. EPDM, ethylene propylene diene monomer, is a rubber-like material. TPO, thermoplastic olefin, and PVC, polyvinyl chloride, are plastic materials. These membranes are lighter and faster to install than built-up roofing and can last 15 to 30 years. Liquid-applied membranes are polymeric coatings that are applied to the roof surface. These membranes cure to form a waterproof layer. Liquid-applied membranes are useful for irregular roof surfaces and for coating over existing roofing. Section 8. Flooring materials. 8.1. Introduction to flooring. Flooring materials must be durable, easy to clean, and comfortable underfoot. Flooring must be resistant to moisture, stains, and wear. Flooring contributes to the aesthetic appearance of interior spaces. The choice of flooring material depends on the application, the climate, the expected wear, the budget, and aesthetic preferences. Different materials are appropriate for different areas of a building. 8.2. Hard flooring materials. Ceramic tile is one of the most durable flooring materials. Ceramic tile is made from clay that is shaped and fired in kilns. The hard glazed surface of ceramic tile resists staining and is easy to clean. Ceramic tile is available in many colors, patterns, and finishes. Glazed tile has a shiny surface. Unglazed tile has a matte finish and slightly better slip resistance than glazed tile. Grout is used to fill the spaces between tiles. Grout can be cement-based or epoxy-based. Cement-based grout is less expensive but more porous and susceptible to staining. Epoxy-based grout is more expensive but more resistant to staining and moisture. Porcelain tile is a denser, more durable form of ceramic tile. Porcelain tile is harder than regular ceramic tile and more resistant to moisture. Porcelain tile is appropriate for wet areas. Stone flooring, including granite, marble, and slate, is durable and has natural aesthetic qualities. Stone is porous and requires sealing to resist stains. Stone can be slippery when wet, particularly marble. Stone is expensive compared to other flooring materials. Stone can crack or chip if subjected to impact. 8.3. Resilient flooring. Linoleum is a natural flooring material made from linseed oil, cork dust, and other natural materials on a burlap backing. Linoleum is moderately durable, biodegradable, and available in various colors and patterns. Linoleum is flexible, providing some comfort underfoot. Vinyl flooring is a synthetic material made from polyvinyl chloride. Vinyl flooring is inexpensive, durable, and easy to maintain. Vinyl is available as sheet goods or as tiles. Vinyl is water-resistant and suitable for kitchens and bathrooms. Vinyl flooring can be damaged by high heat and sharp objects. Rubber flooring is durable and provides good comfort underfoot. Rubber flooring is often used in commercial applications and in areas requiring slip resistance and durability. Rubber flooring is more expensive than vinyl flooring. 8.4. Wood flooring. Solid wood flooring is made from boards of solid wood. Wood flooring provides warmth and aesthetic appeal. Wood flooring can be refinished if it becomes worn or damaged. The surface can be stained or treated in various ways. However, wood flooring is susceptible to moisture damage and cupping or warping if the humidity changes. Wood flooring requires maintenance, including periodic refinishing. Wood flooring is more expensive than many other flooring materials. Wood flooring can be damaged by water. Engineered wood flooring is made from a veneer of real wood glued to a plywood substrate. Engineered wood flooring is more stable than solid wood flooring when exposed to humidity changes. Engineered wood flooring is less expensive than solid wood flooring but is often not refinishable. 8.5. Carpet. Carpet provides comfort underfoot and sound absorption. Carpet is available in many colors and patterns. Carpet is relatively inexpensive to install. However, carpet stains easily and is difficult to clean completely. Carpet can harbor dust mites and allergens. Carpet can deteriorate with wear, particularly in high-traffic areas. Carpet has a relatively short service life, typically 5 to 15 years depending on quality and use. Carpet is typically installed over a cushioning layer called underlayment. The underlayment provides comfort and helps to protect the carpet backing. 8.6. Underlayment. Underlayment is a layer installed beneath flooring. Underlayment provides cushioning and sound absorption. Underlayment can help to smooth out minor irregularities in the subfloor. Underlayment can provide moisture protection. Different underlayment materials are appropriate for different flooring materials. Cork underlayment is natural and provides good cushioning and sound absorption. Rubber underlayment is durable and provides good moisture protection. Foam underlayment is inexpensive. Plywood or other materials can be used as underlayment to provide a smooth, level surface. Section 9. Sealants and adhesives. 9.1. Sealants. Sealants are materials used to fill gaps and create weather-tight seals at joints and connections. Sealants must be flexible to accommodate building movement. Sealants must be durable and resistant to UV radiation, moisture, and temperature extremes. Cork is a general term for various sealant materials. Cork can be made from various materials, including acrylic, silicone, polyurethane, and hybrid materials. Acrylic cork is water-based, easy to apply, and easy to clean up. Acrylic cork is inexpensive. However, acrylic cork has limited flexibility and limited durability. Acrylic cork is appropriate for interior applications with minimal movement. Silicone cork is very flexible and durable. Silicone cork resists UV radiation and extreme temperatures. Silicone caulk is appropriate for exterior applications. However, silicone caulk is more expensive than acrylic caulk. Silicone caulk can be difficult to paint. Polyurethane caulk is flexible and durable. Polyurethane caulk can be painted. Polyurethane caulk is more expensive than acrylic caulk, but less expensive than silicone caulk. Weather stripping is another form of sealant material used around doors and windows. Weather stripping materials include foam tape, rubber, felt, and metal. Weather stripping reduces air infiltration around operable windows and doors. 9.2. Adhesives. Adhesives are used to bond materials together. The choice of adhesive depends on the materials being bonded and the required strength and durability. Construction adhesive is used to bond wood, foam, and other materials in building applications. Construction adhesive is typically polyurethane or acrylic-based. Construction adhesive provides strong bonds and fills small gaps. Construction adhesive can be used to reduce the number of mechanical fasteners needed. Tile adhesive, also called thin-set mortar, is used to bond tile to substrate. Tile adhesive is typically a powder that is mixed with water to create a paste. Tile adhesive is typically cement-based or epoxy-based. Epoxy-based tile adhesive is more expensive but more resistant to moisture and chemicals. Wood adhesives are used to bond wood members together. Common wood adhesives include PVA, polyvinyl acetate, aliphatic resin, polyurethane, and epoxy adhesives. These adhesives create waterproof or water-resistant bonds. Different adhesives are appropriate for different applications depending on the moisture exposure and the curing requirement. Section 10. Summary and conclusion. We have now traveled through the major building materials that form the structures and finishes of modern buildings. We began with concrete, the most fundamental structural material, created from simple ingredients, cement and aggregates, combined in carefully controlled proportions. Concrete is everywhere beneath us. It forms the foundations of buildings. It creates the massive structural elements that carry the weight of entire structures. It is shaped into various forms to serve specific purposes. It develops strength over time through a gradual process of hydration. Understanding concrete means understanding one of the fundamental engineering achievements of the modern age. We then explored steel, the other primary structural material. Steel is strong in both compression and tension. Steel can be formed into slender elements that can span great distances. Steel can be connected through bolting and welding. Steel is vulnerable to corrosion but can be protected through painting, galvanizing, or the use of stainless steel. Steel structures are often elegant and efficient in their design. We examined wood, the oldest building material, still used extensively in construction. Wood is light, renewable, and pleasant to look at. Wood is orthotropic in nature, with different properties in different directions. Wood must be protected from moisture and from decay organisms. Wood has been refined into engineered products that provide more consistent properties and greater efficiency. We studied drywall, the material that creates our interior walls and ceilings. Drywall consists of gypsum core sandwiched between paper layers. Drywall is easy to install and finish. Drywall can receive various finishes and can be decorated easily. Drywall provides fire resistance and sound absorption. We discussed insulation, the material that keeps our buildings comfortable by reducing heat transfer. Insulation works by trapping small pockets of air. Insulation comes in various forms, including fiber-based materials and foam materials. Insulation is installed around building cavities. Vapor barriers protect insulation from moisture problems. We looked at roofing materials, which protect buildings from weather. Roofing materials must shed water and must be durable. Asphalt shingles are the most common roofing material for residential construction. Other materials including wood shakes, tile, and metal roofing are used where their specific properties are valued. Membrane roofing is used on low-slope roofs. We covered flooring materials, which must be durable and easy to maintain. Flooring materials range from hard materials like ceramic tile and stone, to resilient materials like vinyl and rubber, to aesthetic materials like wood and carpet. Each material has specific properties that make it appropriate for specific applications. Finally, we examined sealants and adhesives, the materials that complete the assembly of buildings. Sealants fill gaps and create weather-tight joints. Adhesives bond materials together. Each of these material categories represents decades or centuries of development and refinement. Engineers and scientists have studied these materials, tested them, and optimized them. Building codes and standards have been created to ensure that materials perform safely and reliably. The materials we have discussed are not exotic or mysterious. They are common, ordinary materials found in almost every building. But understanding these materials, understanding their properties, their limitations, and their appropriate uses is the foundation of good building design and construction. A building is only as good as the materials from which it is constructed. When materials are properly chosen, properly installed, and properly maintained, buildings can last for decades or even centuries. When materials are poorly chosen or poorly installed, buildings deteriorate rapidly and fail to serve their intended purposes. The challenge of the builder and the designer is to understand these materials deeply, to know their properties, to know their limitations, to know how they interact with other materials, to know how they change over time, and to use this knowledge to create buildings that are safe, durable, and fit for their purpose. This has been a slow journey through materials. We have not rushed. We have considered details. We have examined specifications and numbers and processes. We have looked at historical development and at modern applications. The world of building materials is a world of precision and order. It is a world where small things matter, where specifications matter, where tolerances matter, where time and process matter. And this, perhaps, is the most relaxing aspect of studying building materials. Everything is knowable. Everything follows rules. Everything can be measured and specified and controlled. There is an order and logic to it all. As you rest now, you might find your mind settling into a peaceful state. The specific details you have heard about materials and processes and specifications create a sense of calm and order. The world feels more predictable and manageable when we understand how things are constructed. Sleep well, knowing that the materials around you, the concrete and steel and wood and drywall, have been carefully engineered and tested and refined over many years. They are strong, they are reliable, they will protect you as you rest. Thank you for listening. May your sleep be deep and restful.